So let's talk a little bit more about interest rates, and specifically the differences between simple interest and compound interest. So let's look at an example. We've got a 20-year-old student who wants to save $5 a day for her retirement. So every day she places $5 in a drawer, and at the end of the year, actually each year, she invests the accumulated savings for that year, which would be $1,825 a year, in a brokerage account with an expected annual return of 8%. So our question is, this is for retirement, how much money will she have when she's 65 years old? So we're looking 45 years out. So what she's doing, and it's a little bit confusing because of the whole $5 thing, but you really want to ignore that and just think about the $1,825 that she's actually investing each year. So she's making a payment of $1,825 a year for 45 years. So what we want to solve for is the future value to know how much she's going to have when she's 65. So at 8%, if 45 is in, 8 is the interest rate, she's starting off with nothing, so the present value is 0, and her payment again was negative $1,825. That's going to give her $705,373 when she turns 65. So now, remember, she was 20. What if she doesn't get started when she's 20 and she doesn't start until she's 40? So now she only has 25 years to save instead of 45 years to save. So we're going to switch in to 25 instead of 45, and look what a difference it makes. So it's still compound interest, but because our N changed from 45 to 25, she only has $133,000 instead of the more than $700,000. So it's $571,954 less than if she had started when she was 20. So now, let's say that instead of it's that same person just wondering what would happen if she waited until she was 40, or I guess you could still say that. What if she waited until she was 40, but she still wanted to have more than $700,000 when she turned 65? How much would she have to pay or deposit or invest each year? It was $1,825 if she starts when she's 20. Let's solve for the payment. Given that our N is 25 years, interest rate stays the same, present value is still 0, but we want to have the same future value. Now our payment has gone from $1,825 a year to more than $9,600 a year. Now, let's look at uneven cash flow streams. So we've been talking about annuities where the payment is the same each period. If it's not the same, then we can't calculate it as an annuity. Now we have an uneven cash flow stream, and we're going to have to use our cash flow worksheet. So here's an example of an uneven cash flow stream. We have 4 cash flows, but they're different. We get $300 twice, but we also get $100 and we have a negative $50. So this is not an annuity. So back in the old days, what I had to do to figure out a problem like this is I would calculate the present value of each one of those cash flows individually and then add them all up. And then I could get the present value of that stream of uneven cash flows. And so that's what you see here. The present value of $100 at 4%, remember we call this discounting, is $96.15. Present value of the $300 is $277.37. Now, why aren't they the same? You know that, right? Because the N is different. Because the first $300 you're going to get in 2 years, the second $300 you're going to get in 3 years, so it's going to be worth less than the $300 that you get in 2 years. So we continue that until we discount all of the future cash flows, add them together, and that's the present value of the stream. In our calculator, we can use the cash flow worksheet. So if you get your calculator out again, you're going to hit this cash flow button, which is right next to the second button. When you bring up the cash flow worksheet, it will ask you for cash flow 0, cash flow 1, and so on. Now what they're not showing here is that once you get to cash flow 1, 2, 3, and 4, and so on. After each cash flow, it's going to ask you for the F. So it'll say cash flow 1, you put in $100, press enter, and then you hit the down arrow key, and then it's asking you for F1. F1 is the frequency. So it's asking you how many times are you going to get $100. Well, in this case, you're just going to get it one time, and that's the default. So you press enter and the down arrow. But now for cash flow 2, you've got options here. You could put in that cash flow 2 is 300, press enter, down arrow, and you could say the frequency is 1, enter down arrow, and then go on to cash flow 3 and make that 300 also. Or for cash flow 2, you could say the frequency is 2, enter down arrow, and then go on to that negative $50, whichever makes sense to you. If you use the frequency button, it will make your life a little bit easier. You just have to make sure you remember that you did that. Once you get all the cash flows in, you're going to solve for the net present value. So you'll hit the NPV button. After you hit the NPV button on your Texas Instruments calculator, it's going to ask you for the interest rate. So the I equals will pop up in your screen. When you get that, just put in 4, enter, down arrow, and then hit compute. And you'll get the same answer that we saw a minute ago. So now, some questions to make sure that you're following what we're talking about. Will the future value of a lump sum be larger or smaller if compounded more often, holding the interest rate constant? So up to this point, we've been talking about annual compounding, but now we want to talk about quarterly compounding or semi-annual compounding or even monthly compounding. I know I was jumping around a little bit there. But the question is, when I go from annual compounding to semi-annual to quarterly to monthly, will my future value get bigger or smaller? What do you think? Well, it's going to get bigger, because what that means is that I'm getting interest more often. So the more often I'm getting interest on interest, the greater my future value will be. So here's an example. First, with annual compounding, $100 grows to $112.49 at 4% over 3 years. But if I earn interest semi-annually or twice a year, I'm getting 6 interest payments instead of 3, and so I'm getting an extra 13 cents at 4% annually. Because if you notice, 4% annually is 2% semi-annually. So we didn't change the problem, but we had to cut that interest rate to make it a periodic interest rate. And we've got 2 interest payment periods per year. So we take 4 divided by 2 to get 2. But then also notice we have to increase our number of payments. So we take 3 years times 2 payments per year, and that's where the 6 comes from. So now a little bit more on interest rates. You've got to keep all these terms straight. So one is a nominal rate. So we hear it called nominal rate, or sometimes quoted rate, or sometimes stated rate. Whatever you call it, this rate doesn't care about compounding. So you might hear someone quoted as 4% compounded quarterly. So the 4% doesn't take into consideration the compounding, but you can, because I'm getting ready to show you how. The periodic rate was what we were just talking about in that last example with semi-annual compounding. So the periodic rate is the monthly rate or the quarterly rate or the semi-annual rate. So we take that nominal rate and we divide it by the number of compounding periods in a year. So here's where I show you how to take the compounding frequency into consideration on your interest rate, because we said nominal rates don't take into consideration compounding, but this effective or equivalent annual rate does. So now here's a kind of a funky formula to show you how to do it. I'm going to show you on your handy dandy calculator. So in this example, we have a 4% stated rate, and we have a compounding frequency of semi-annual. So you already know here that the answer, the effective annual rate, when you take into consideration semi-annual compounding, is 4.04%. So let's do this on the calculator. Hit your second key and the number 2, because if you look just above the number 2, it says ICONV. That stands for the Interest Conversion Worksheet. So what I'm going to do, I only have 3 things to put in here, so I've got to put in 2 and solve for the third one. So first it's going to ask me for the nominal rate. Remember in this example it's 4%, so I'll hit 4, enter, and then I'll hit the down arrow key. Now it's asking me for the effective annual rate. Well, that's what I want to know, so I'm going to hit the down arrow again. Now it's asking me for C/Y. That's the number of compounding periods per year. Remember in this example we have semi-annual interest, so that's 2 compounding periods per year. So I'm going to hit 2 and enter. Now I'm ready to compute the effective annual rate, or the EAR. So I'm going to hit the up arrow to go back to EFF, or I can just keep hitting down till I get back to EFF. But once I have EFF in my window, I'll hit compute. And if you did it right, you'll have 4.04%. So now that you know how to calculate an effective rate, why do you care? Well, you care because compounding makes a big difference. In that last example, we only had semi-annual compounding, but what if it's quarterly? Or what if it's monthly? Or what if it's daily? That interest rate is going to get pretty high. So the difference between the nominal rate and the effective annual rate is going to grow as the compounding frequency grows. And so another practical reason why we care about this is sometimes we might be comparing opportunities that have different compounding frequencies. And so the EAR puts them on equal footing. So it takes into consideration compounding frequency no matter what it is. So now I could line up all my opportunities and look at the EAR of each one, and now I'm comparing apples and apples, or oranges and oranges. So why is it important to consider effective rates of return? Well, take a look at this. This was what I was mentioning a minute ago. In our example, we had a 4% nominal rate, which is equal to the annual rate, but it came out, we just calculated it, as 4.04 semi-annually. Look at how it continues to grow. 4.06 quarterly, 4.07 monthly, 4.08 daily. Now, if we had a higher annual rate, these differences would be even greater. So it makes a difference how frequently you're going to earn interest. So when is each rate used? Now we've talked about the nominal rate and the effective rate. So the nominal rate is what's going to be in contracts. It's what banks will quote, and what brokers will quote. But typically it's not what we use in a calculation. In calculations we're going to use the periodic rate. I was hesitating a moment ago because actually there is one time where we're going to use the nominal rate in calculations, and that's when the compounding frequency is annual, right? Because when the compounding frequency is annual, the nominal rate is equal to the periodic rate, because the periods, there's one period per year. The periods are years. So the periodic rate is what we use in calculations and show on timelines, and the EAR is what we use to compare investments with different payments per year. So now let's take another example. What's the future value of $100 after 3 years under 10% semi-annual compounding or quarterly compounding? So here's a formula for future value taking into consideration the compounding frequency. So a compounding frequency other than 1. Or you could use it if the compounding frequency is 1. Then M will be 1. So I think this is the example we saw just a moment ago, where we had semi-annual compounding and then we had quarterly compounding. So with semi-annual compounding, the future value is 112.62. With quarterly, it's 112.68. And let's go back to that one for a second. So in the financial calculator, what we're going to do then is, let me get this going on my calculator. What we're going to do for semi-annual compounding, now our N is going to be N times M. So it's 3 years, 2 payments a year, so N is 6. And the interest rate will be the interest rate divided by M. So 4 divided by 2 is 2. And the present value is 100. 0 payment, compute future value. And so now with quarterly compounding, what we'll do is we'll change N to 12 and I to 1. So can the effective rate ever be equal to the nominal rate? Yes, but only if the annual compounding is used. So M is equal to 1. So in that case, the effective rate, the nominal rate, and the periodic rate would all be 1. So if M is greater than 1, the effective rate will always be greater than the nominal rate. So here's another one. What's the future value of a 3-year, $100 annuity if the quoted interest rate is 4% compounded semi-annually? So this means that we've got 2 payments a year for 3 years. And those payments are $100, so we could calculate the future value of each one of those payments and add them together. So our result would be $312.28. Or in our calculator, N is going to be equal to 3, and for our interest rate, we use the EAR. And present value is 0, payment is negative 100, and compute future value. And then this is just the same way in reverse, solving for the present value.